Thank you very much for kind introduction. I'm Shinpei Yamamoto from AIST. First of all, I'd like to thank my thanks to the organizing committee, especially Hayase Sensei, for giving me a chance to present our work. Today, I'd like to talk about the synthesis of the silicon dioxide, silica-coated alpha ion nanoparticles at low temperatures. Okay. At first, I'd like to show acknowledgement. The work presented today are based on the collaborative silicon dioxide, silica-coated alpha ion nanoparticles at low temperatures. Okay. At first, I'd like to show acknowledgement. The work presented today are based on the collaboration work with, sorry, it's difficult to control this one. Results obtained with the collaboration work with these collaborators. The work presented today obtained during the period I belong to Kyoto University. And the work presented today also obtained with part of the results obtained with the support of these funds. I'd like to show my thanks to the collaborator and the money. Okay. Here shows the outline of my talk. I'd like to talk about mainly three topics. One is the introductory part. I'd like to talk a basic concept about nanoparticles. And the other two are the scientific topics. And finally, I'd like to summarize my talk. Okay. Okay, now let me start the general introduction about nanoparticles. So, what is nanoparticles? Let me start my talk with this very simple questions. We often hear the word nanoparticles, but if we are asked, what is nanoparticles? You may think about a little bit how to answer. Then I'd like to explain some common senses about nanoparticles. Okay, so as you know, the word nanoparticle consists of the prefix nano and the word particle. Of course, you know the meaning of the word particle. Then, how about the meaning of the prefix of nano? Of course, we often see this prefix nano. For example, this is a flyer of this symposium. Here, of course, we see the prefix nano. What is nano? The prefix nano is derived from a Greek word, nanos. And it has a meaning of the extremely small. Yes, it's very small. Then, how small? Yes, nano can be used as a prefix for any unit to mean billions of that unit. So, for example, 1 nanometer is equal to 10th to the power of -9 meter. Yes, nano is very small. Then, what is a nanoparticle? Although there are no common senses, clear definitions about the nanoparticles, but it is widely accepted. Nanoparticles are particular objects with characteristic dimensions in the ranges between 1 to 100 nanometers. Okay. So in the previous slide, I explained nanoparticles are the particular object with characteristic sizes in the range of from 1 to 100 nanometers. Then how small or how big they are. In this slide, I'd like to show the size of the other object in order to better understand the size ranges of the nanoparticles. Okay. As you can see here, the smallest building block is usually the atoms. The size of the atom is around 0.1 nanometers. And when the atoms gather to form an aggregate, they are often called cluster or molecules. If the atoms forms an aggregate is metal and the main group element, they are often called cluster. And if the atoms forms an aggregate is mainly from the main group element, they are often called molecules. And the sizes of the clusters and the molecules are around 1 nanometers. And when the molecules gather, they are called polymer or the biomolecules. As you can see, their size is just within the nanoparticle size ranges. And the particles that are bigger than 100 nanometers are often called as colloid. We often refer to a hair as a representative of a small object, such as, okay, this is smaller than a hair. However, as you can see, the typical width of the hair, human hair, is around 100 micrometer. It's too big if we think about the nanoparticle world. So for me, so the hair should be a representative of a big object, not small ones. Okay. So, okay, in the previous slide, I compared the size of the nanoparticle range with the other object. I hope now you can better catch how big or how small the nanoparticle range is. Yes, they are very small. And in the following slide, I'd like to explain how to prepare such a small object. There are basically two methodologies. One is the bottom-up approach. In this approach, this approach uses smaller initial object, such as atoms, to build up to the nanoparticles. Typical examples of this bottom-up approach is the chemical synthesis, and the electroplating method Yanai sensei talked about also belong to the chemical method. And the other methodology is the top-down approach. In contrast to the bottom-up approach, the top-down approach uses a larger initial object here, such as bulk materials, which can be broken into smaller pieces. The top-down approach includes the ball milling and inert gas condensation or something else. Many methods belong to this approach. Okay, in the following slide, I'd like to explain some of the preparation methods. So the first example is the ball milling. And the ball milling is a kind of a grinder. So here shows a schematic view of the ball milling facilities. It consists of hollow cylinders rotating with the axis. And during the rotation, the starting materials are grinded with many spherical balls made of the hard ceramics. So here shows schematic view of the grinding. Anyway, so by using the balls, and the initial larger particles are broken into smaller pieces. That's the principle of the ball milling method. And the next example is another example is the inert gas condensation method. Here shows a schematic view of this method. In this method, the evaporated metal atoms from the cold hot sources, like here, the evaporated metal atoms collide with the cold inert gas atoms in the chamber to lose their kinetic energy and form nanoparticles. Yeah, here the evaporated atoms, they lose energy and form an aggregate, then weak. Yes. This method has been widely used to prepare fine metal nanoparticles from 1930s. Yes. Here shows some examples of the nanoparticles prepared by this method. As you can see, not only for the pure metals, but also for the alloy nanoparticles can be prepared with this method. Okay. So now I'd like to talk about the chemical method. The first example is the flame pyrolysis method. Here shows a schematic view of this method. So this method produces metal oxide nanoparticles from highly volatile gaseous metal precursors that are decomposed and oxidized in the flames. This is the flames, yeah, to form metal oxide nanoparticles. Okay. This method has an advantage to be easily scaled up. And actually, the mass production of the metal oxide nanoparticles with this method is done. So here shows a typical example of the metal oxide nanoparticles prepared by this method. Anyway, so this method is very good to prepare the metal oxide nanoparticles. However, of course, it can be used carbide or some kind of the nanoparticles. Okay. Another example is of the chemical synthesis is the liquid phase synthesis method. As shown here, so this method carried out the reactions in the liquid phase. And this method produces nanoparticles using a variety of the precursor reagents that are decomposed and reacted in a liquid phase with the presence of the surfactant. So with this method, we can get nanoparticles coated with a surfactant. So because of the presence of the surfactant, they form well-dispersed state in order to be carried out to the reaction homogeneously. So, and this method is very attractive because structure of the nanoparticles are relatively easy controlled, especially if we carried out the reaction at high temperatures using the high boiling point solvent, typically more than 300 degrees Celsius or something else. We can finally control the structure of the nanoparticles. Here shows an example. This is a case of the iron oxide nanoparticles. As you can see, the size of the nanoparticles are controlled in 1 nanometer scale. Okay. Anyway, so this method is very interesting and has a lot to be explained. But because the time are limited, I'd like to skip. And so maybe the next speaker, Ogawa Sensei, deals with nanoparticles prepared in the liquid phase. So I hope he will explain a little bit more about this method. Okay, so now let me stop the introductory part and move on to the scientific topic. And the first scientific topic I'd like to talk about is the alpha ion nanoparticles coated with SiO₂. Okay. So let me start my scientific talk with this beautiful picture. This is a Lady Elliot Island in Australia. And this island located in the Great Barrier Reef areas. Okay. As you can see, this island has the surrounding corals, and here is the land part, and of course, important facilities such as airport, hotels, restaurants, and even the birds are on the land side. Okay, so and also this, as I explained, this island is very famous for its beautiful corals around here. Okay, so here shows a cross-sectional view of this structure of this kind of island. As you can see, the most important point of this kind of the structure is the land part is surrounded by the corals, like this. So because the land part is surrounded by the corals, so the inner reefs here are very calm, even if the outside sea is very rough. This is, if we say in other words, the most important part of the island, this land part, is protected by surrounding coral reefs. The nanoparticles I'd like to talk about today has a similar structure. That is, as shown here, the alpha ion nanoparticle here, it is a most important point of our nanoparticle is surrounded by the protective layer of the SiO₂. I hope you can feel the similarity in between these two structures that I felt. Okay. Anyway, so, here again the title of my presentation. Now I hope you can better understand quartz, the alpha ion nanoparticles coated with the silica. Yes, this one. But I hope now you have next questions, as shown here. Okay, why you selected the ion nanoparticles? Why coated with the SiO₂? How to synthesize? Okay, you said low temperature, but how low it is? In the following slide, I'd like to answer these questions. Okay, let me first explain why I chose alpha ion nanoparticles. Because as you know, so the alpha ion is known to have very high saturation magnetization of about 200 to 2 EMU per gram. And that is more than twice of the conventional magnetic material of the iron oxide, magnetite. And alpha ion is known to have rather soft magnetic properties and easy to be saturated even with a small magnet. Yes, alpha ion has many good points. Of course, they have disadvantages. The biggest disadvantage of the alpha ion is ion rust. Namely, the alpha ion is very easy to be oxidized in air. Okay. This tendency, easy to be oxidized, is especially prominent for the case of the nanoparticles because they have large specific areas. Here shows a TEM image of the alpha ion nanoparticles I synthesized. They are diameter around 10 nanometers or so. If we expose these nanoparticles to air, what happens? You may imagine they will burn immediately. So it's a big problem because we want to find an application of the alpha ion nanoparticles in air. We should solve this problem. There may be several answers. The answer we selected is here. We coat the surface of the alpha ion nanoparticle with some kind of the protective layer. If we can realize this kind of the structure, we can expect this kind of nanoparticle can have large saturation magnetization arising from the metallic ion core and moderate resistance against oxidization, which arises from the SiO₂ shell. Okay, now we set the goal, this structure. Then the next question is how to prepare. Of course, there are several methodologies we can think about. But we selected this methodology, namely reducing the iron oxide nanoparticles coated with the SiO₂. To go there. So we chose this methodology because this method doesn't have this method has no processes which deal with the very dangerous bare iron. We thought it's a very big advantage if we think about scaling up of the preparation. Okay, so at first we tried this way, this reduction, by using the hydrogen gas. Of course, as you know, the hydrogen gas is the most popular reductant, and I think the first to be tried. Okay, here shows the results. Okay, here shows the XRD patterns of the samples after the hydrogen gas treatment at different temperatures. From this figure, we can know at first at the temperature less than 600 degrees Celsius, no reduction occurs. So we have to increase the temperature because we wanted to carry out the reduction. Second, at the temperature of the 650 degrees Celsius, now we can see the diffraction peaks from the alpha ion phase. However, as you can see that there still remains the diffraction peak from the starting oxide. Namely, at these temperatures, the reductions are incomplete. So we have to further increase the temperature. And at 800 degrees Celsius, Now we can only see the diffraction peak from the alpha ion phase. However, as you may find, the width of the diffraction peak is very narrow. This means the formed alpha ion particle is very big. So, namely, at this temperature, we can obtain a complete reduction, but grain loss due to the aggregation occurs. So, because of that, we want to get this kind of the reduction style, namely, I want to finish the reduction with iron oxide nanoparticles just within SiO2 core. So, however, if we use hydrogen gas, we have to carry out the reaction at 800 degrees Celsius. Otherwise, we cannot complete the reduction. But this temperature is too high to keep the isolated particle shape. That's a big problem. How to solve? One possible answer is to lower the reduction temperature by using a stronger reductant, pitch wax at low temperatures. This is the reason we focused on the reduction reaction using the calcium hydride, CaH2. For most of the people here, so the CaH2, calcium hydride, is, how to say, unfamiliar material. Okay, but however, nowadays, so the calcium hydride are used in the rational material synthesis. Some examples are shown here. Okay, anyway, so the most important feature of the reaction with the calcium hydride is we can get very strong reducing ability, especially at low temperatures. So we want to take this advantage. Okay. Here shows the purpose of this part. It's very simple. So that we want to realize this very simple scheme by using the CaH2. In other words, we can complete the reduction reaction within the SiO2 shell by using CaH2. Okay, here is the introductory part of this one. And okay, next I'd like to show the results. But before that, I'd like to briefly explain what kind of the experiment we carried out. The first process is the preparation of the iron oxide nanoparticles coated with the SiO2. At first, we prepared the iron oxide nanoparticles by using iron 3 orate as a source of the iron, oleic acid as a surfactant, and some solvent. And we used the trinormal oxylamine as a solvent. Their boiling point is about 350 degrees Celsius or so. Here shows the typical thermal image of the iron oxide nanoparticles we prepared. Then we coat the surface of the nanoparticles with SiO2. And as this expanded view shows, the black spot here is the iron oxide nanoparticles, and the surrounding shell, gray shell, is the SiO2. Okay. So now we have the iron oxide nanoparticles coated with the silica. The next step is the reduction with calcium hydride. Because calcium hydride reacts with the moisture in the air, we mix the calcium hydride and the iron and the SiO2-coated iron oxide nanoparticles in a globe box. And then we seal the mixture in an evacuated glass tube. And finally, we carried out the heat treatment. And the typical conditions are at 300 degrees Celsius for 19 hours. Okay, so through this way, so that we prepared the samples. Okay, now I'd like to show the results. But first, I'd like to talk about the changes in the crystal structure. Okay, here shows the XRD pattern and the thermal image of the sample before the reduction. From this thermal image, as you can see, the samples has nice particular shapes. And from the XRD patterns, so you can see the broad diffraction peak arising from the amorphous SiO2 shell and the other diffraction peaks from the Fe3O4. With this sample, we tried a reduction. Okay, here shows the XRD pattern and the TEM image after the reduction. As you can see, the TEM image after the reduction, still the sample, as you can confirm, still the sample has nice particular shapes, very similar to the starting materials. However, the XRD patterns are completely now different. Of course, you can see the broad diffraction peak from the amorphous silicon, but now you can see only 3 peaks, all of that assigned to the alpha ion. Okay. So with these results, now we can say we can get alpha ion nanoparticles with well-defined morphologies. So in this slide, you may find an interesting feature of this method. This is, as this close-up view shows, our nanoparticles consist of the alpha ion core and the SiO₂, but we have voids inside the SiO₂ shell. Here, this brightest areas in between ion and SiO₂ is the void. Why the void forms? Because we carried out a reduction reaction. The reduction reaction, in other words, is a reaction that removes the oxygen atoms. Because now we carried out the reduction of the core nanoparticles, so during the reduction, the starting core ion oxide nanoparticles lost their oxygen atoms. So the polymer shrinkage takes place. Now we see the void. Okay, this is a very interesting feature of our reaction. Okay, here shows a high resolution TEM image of the alpha ion nanoparticles. As you can see, the nice atomic images can be observed throughout the nanoparticles, and no grain boundaries are there. So from this result, the alpha ion nanoparticle formed is a single crystal of the alpha ion. We know. Okay, so in this slide, I'd like to talk about a little bit details of the changes in the morphologies. Here again, TEM image of the sample before the reduction. The sample before the reduction has 2 characteristic sizes. One is the size of the core, D core. And the other is the size of the overall particle size. So they are about, the D core is about 25 nanometers, and the DO is about 58 nanometers. Okay, we carried out the reduction. Okay, here again the same TEM image after the reduction. Now we have a new characteristic size. That is the size of the void. As I explained in the previous slide, this void formed because of the volume shrinkage during the reduction. So the size of the void is expected to be the same as the size of the core before the reduction. How about the results? Okay. Here shows the size of the void. Anyway, as you can, the size of the void is about 25 nanometers, which is in good agreement with the size of the core before the reduction. Anyway, so as I explained, with this reduction method, we can get nice alpha ion nanoparticles with nice particular shapes. But this method enables not only to keep the particular shape of the nanoparticles, but also keep the very fine structures of the starting materials. This is a very big advantage of our reduction method, I think. Okay, here I'd like to talk about the magnetic properties. At first, I'd like to talk about the microscopic magnetic properties. Okay, so we carried out a Mossbauer spectroscopy measurement. As you know, Mossbauer spectroscopy is a very sensitive tool about the microscopic environment of the ion atoms. And we here show the 2 results. Results from the 2 samples. One is from the one has the small ion core, the other has a big ion core. Here shows the results from together with the feed. As you can see the results, the data are well fitted by single alpha ion pattern. I will skip the details, but here shows the fitting parameter used to fit. Sorry, the close resemblance of the value of the hyperfine field reveals, so the obtained alpha ion nanoparticles is very, the quality of the alpha ion phase was very good. Okay, so here, okay, I'd like to talk about the macroscopic magnetic properties. And the samples are again the small one and the big one. Here shows the hysteresis loops measured at room temperature. Okay, also this is normalized ones, but we can estimate the saturation magnetization of the alpha ion core. Its value was about 210 EMU per gram. This is very close value to the literature value of the bulk alpha ion. So with this data, we can also say the formed nanoparticle is a very good alpha ion. Okay, so now we have a good alpha ion. And we coated their surface because we wanted to get the resistance against oxidization. How about the work of the SiO₂ shell? Here shows the time evolution of the saturation magnetization of the sample after exposure in air. Because so if the alpha ion oxidized, the saturation magnetization will be lowered. So as you can see, for this case, the smaller sample, we can see the saturation magnetization is decreasing upon exposure to air. So the samples are oxidized even if they are coated with SiO₂ shell. This is because, as I explained, so the surface of the alpha ion nanoparticle is coated with silica, but the silica is in amorphous state. As you know, the silica in amorphous state has many open micropores through which the gaseous molecules can pass. So our nanoparticles are oxidized in air even if they are coated with SiO₂. So the problem is, so the matter is how the degree of the oxidization. For the case of the small sample, the sample still has the more than 60% of the initial value. So, okay. Even if I stress this sample has more than 60% of the initial value, they are oxidized. I agree. But so please remember the fact. If we expose the bare uncoated ion nanoparticle to air, they will immediately burn. So if you keep this in mind, you may allow for me to say our nanoparticle has a moderate resistance against oxidization. Okay, so in the previous slide, I said the surface of the nanoparticles are oxidized upon exposure to air. Here we checked the surface oxidized layer by means of the high resolution TEM measurement. Here shows the high resolution TEM image after 10 days exposure in air. As this close-up view shows, we can see the nice lattice images throughout the nanoparticles. Okay, so the first Fourier transform, a 50 image of the inside the core is shown here. As you can see, this F50 image consists of only the spot from the 110 lattice of the ion. However, an F50 image from the surface areas of the nanoparticles. Of course, we see the spot from the 110 lattice of the alpha ion. However, we also see the 111 a spot from the 111 lattice of the FeO oxide phase. So with this result, so we don't know the details about the oxidized layer, but we can say at least so the surface oxidized layer contains the FeO phase. Okay, here let me briefly explain the reduction processes. In order to study the reduction processes, we carried out in-situ XRD measurement. Okay, here shows the results from the smaller samples. I will skip the details, but the starting gamma ion oxide was reduced to Fe3O4, FeO, and finally to the alpha ion. Here shows the results from the other samples, and it has a rather bigger particle shape, and the starting phase is alpha ion. However, anyway, it is reduced to the Fe3O4 and finally to the alpha ion. If we compare these results, you may feel so the reduction processes are very similar. Yes, it is very similar, but there are several differences. One of the biggest differences are the formation of the FeO phase or FeO4 phase. This was only observed in the smaller samples. This is probably because the FeO is a metastable phase, and the stability increases with decreasing particle size. So that's because this sample has a very big particle size, and the FeO is unstable, and they cannot exist, and the FeO phase cannot exist. Okay. As you know, the magnetic properties of the nanoparticles are strongly depend on the particle size, and we tried controlling the particle size, as shown here. Okay, here shows the thermal image of the ion oxide nanoparticles with different sizes. Of course, we can reduce this one to form the alpha ion nanoparticles with different sizes. Okay, now let me briefly summarize this part. Okay, as I repeatedly said, now we have the alpha ion nanoparticle coated with the SiO2. And we confirmed reduction temperatures can be as low as 200 degrees Celsius. And our nanoparticles have moderate resistance against oxidization. Yes, now we have this kind of the nanoparticles. Then what should we do? And what we did was to find the application of our nanoparticles. So this is the last topic of my scientific talk. And in this part, I'd like to talk about our trials to find possible applications in the biomedical field. Okay. Yes, so as I repeatedly explained, we have the alpha ion nanoparticles with large saturation magnetization and rather soft magnetic properties. How to utilize such properties? Here shows a typical situation induced by the magnetic materials. For example, this is a situation pachinko balls are attracted by a permanent magnet. Of course, you know this occurs. It's natural. But this picture shows a very important feature of the magnetic material that is attracted by a permanent magnet. By using this property, we can do magnetic separation of the important materials. Okay, so with this slide, you may feel nostalgic. I think so that maybe you saw this kind of the structure in your primary school days. This kind of the structure formed if we place an iron sand around a bar magnet. This line-like structure is called magnetic field line. In Japanese, jiryokusen. And the present so that this figure reveals this fact, namely, and around the magnetic material, there is a local magnetic field. And this property was used in the magnetic resonance imaging as a form of the contrast enhancing agent. And this slide shows the magnetic material can generate heat in AC magnetic materials. AC magnetic field. And this property was used in magnetic hyperthermia, which is a method to be expected to be good for the cancer treatment. So anyway, there may be many applications which use the magnetic nanoparticles. However, among them, we focused on the applications in the biomedical areas because of the intrinsic properties of a magnetic field. That is, our tissues, our human bodies are transparent to the magnetic field. Because we know the fact, we cannot see the object behind me. So, as you cannot see the slides. That is because the light cannot pass through our human body. Actually, the penetration depth of the light is less than a centimeter. However, in case of the magnetic field, situations are very different. We know we can get information about any organs in human body by using an MRI method. This is because our human bodies are transparent to the magnetic field. Actually, the penetration depths are very big. So if we use a magnetic field, we can reach any organs in a human body. It is a very big advantage if we think about the biomedical applications. So by taking this advantage, some cutting-edge medical technologies are proposed. And one is the detection and the killing solid tumor. If we use the magnetic nanoparticles, which can accumulate the tumor site, we can, of course, visualize where the tumor is, and we can cure the solid tumor by using the heating, a magnetic hyperthermia method. Another application, another one is the magnetically guided drug delivery. As I explained, magnetic materials are attracted by a permanent magnet. So in this sense, if we use a drug-loaded magnetic nanoparticles, they can be transferred, delivered to the specific site, we hope. So these technologies are so nice, but haven't been realized yet. Why? Of course, there are several reasons, but in the following, I'd like to explain some reasons which relate to the material aspect. So in this slide, we'd like to think about by what performances in these applications are determined. The answer is the saturation magnetization. Saturation magnetization has very big effect on the performances in these applications. For example, in this magnetically guided DDS, performances are proportional to saturation magnetization. Situations are same in case of the magnetic hyperthermia. In case of the MRI method, and the effect of the saturation magnetization is further big. Performances are proportional to the square of the saturation magnetization. So if we want to get better performances in these applications, we have to use the magnetic nanoparticles with high saturation magnetization. Then what is the saturation magnetization? This is the maximum value of the magnetization and intrinsic properties of a material. So if we want to get magnetic nanoparticles with high saturation magnetization, we have to prepare magnetic nanoparticles with high saturation magnetization materials. Okay? Here shows the typical saturation magnetization of the MRI agent now clinically used. They are made of the iron oxide nanoparticles. How big the saturation magnetization of iron oxide is? Unfortunately, they are not so big. Of course, there are the classes of materials with larger saturation magnetization. They are the metals and alloys. Sorry. As explained, a certain composition of the iron cobalt alloys has very high, the largest saturation magnetization. So this material seems to be good for the biomedical applications. However, the cobalt is known to be a toxic element of our human, so we cannot use such materials. Then the alpha ion seems to be better, if the second choice, but seems better because they have large saturation magnetization and alpha ion, metallic ion is not toxic element to human body. Then, yes, we have alpha ion nanoparticles. How about our nanoparticles for the biomedical applications? The answer is no, unfortunately, because of the alpha ion nanoparticle alone is not enough. So we need proper surface functionalization for the applications in the biomedical field. And we decided to develop a method for surface functionalization. Okay, sorry, again, this picture. I repeatedly said, now we can prepare the alpha ion nanoparticles coated with the SiO2. The important point is we can achieve this at low temperatures. In this case, 200 degrees Celsius. So the 200 degrees Celsius is not so high temperature, even for certain class of the organic molecules. So we decided to carry out this kind of modification. Namely, we we modified the surface of the sample before the reduction, and we carried out the reduction reaction. Because the temperatures are not so high, we expect surface organic molecules can survive even during the reduction reaction. Okay. So then I'd like to show the result. This strategy can work or not. Here shows the cases of this kind of alkyl chain modified samples. Okay. Here shows the TEM image and the XRD pattern before reduction. Okay, this is the TEM image and the XRD pattern after the reduction. Okay, particle shapes are okay. We can see the formation of the alpha ion. Then, how about the surface organic molecules? We carried out an IR study, infrared study. Here shows the infrared pattern before the reduction. We can see the absorption peak from the alkyl chain here. Okay. Then after the reduction, what's the pattern? Of course, as we expect, the absorption pattern from the surface alkyl chain still arrives. Okay, with these results together, now we can say this kind of strategy can work. Okay, so because of the sample after the reductions are modified with alkyl chains, they can form stable dispersion in non-polar organic solvent. This is the image of the battle of the chloroform. Okay, so anyway, in the previous slide, I explained the cases of the alkyl chains, but the range of the surface functionalities are not limited to that. Here shows the other examples. For example, we can get the PEG, polyethylene glycol modified samples. This is a TEM image. So because, as you know, PEG is a biocompatible polymer and has the stressless, to the intravenous administration. And we can also get an COOH surface. So as you know, the COOH functionality can be used to introduce other functionality on the basis of the well-established protocols. Okay. Because of that, I'd like to use our nanoparticle in biomedical applications. Cytotoxicity, or how safe our nanoparticle is a very important issue. We checked the cytotoxicity of our nanoparticles. We used this COOH modified ones. And the results from the clinically used MRI agent are also shown here. In this slide, the horizontal axis represents the amount of the doped nanoparticles in the form of the concentration of the ion element. The vertical axis represents the viability. Okay, how safe the nanoparticle is. So in this slide, the higher the viability, the safer nanoparticle. As you can see, our nanoparticles are as safe as the clinically used ones. Okay, so this is the last slide of my presentation. Thank you very much for staying wake up. And okay, I welcome your comments and questions. Thank you very much.